to define clearly in terms of the elastic region, right? If you remember your stress strain curve, you have a elastic and somewhat the non-elastic curve. All right. So in this portion, we're going to talk about the elastic region. All right, to somewhat define to you the stress of a bar. Okay, to define the stress of the bar. You know that the stress is equals to E the Young modulus times the strain. So you know that this strain this little extension over here due to a certain stress is du. We call this a du, and we call this original length the dx. So the strain itself by definition is a small changes of L divided by L, which is a small changes of the length, which is du, over the whole original length of L, which is dx. Alright, so the original length is this one, a small change is du, so a small change divided by its original length, I think you get what I mean. Okay, so therefore we have the strain is equals to du dx. So this is the first step. The second step, stress is equals to E du dx. Alright, and from the previous video, you just take a look, U is equals to N1 U1 plus N2 U2. Right, if you still remember. Alright, so therefore in such the case that happens, you know that the whole overall displacement is in terms of the M1 U1 plus N2 U2. Okay, so just simply sub in U as this portion over here. So what I have is simply E over dx first. Alright, and then sorry, I should have write it as E d dx, and then the whole thing, this U, I'll just sub it as this stuff over here. So you give me a while. After which we can multiply in the d over dx. What do we have is equals to E, alright, dn1 dx u1, okay, which is this thing multiplied by this thing. Okay, hope that this is pretty clear, plus dn2 dx, which is d over dx times n2, alright, and then u2. Okay, and then I can simply rewrite them in terms of a matrix. Okay, by same I'll just keep this E over here. Alright, I can rewrite this thing in terms of a matrix. Alright, we know that the strain displacement is equals to dn over dx. Alright, so in this case we just write it as b1 and b2. Okay, so what we have is b1 b2, okay, and then we have u1 u2. Okay, so this is b transpose, this is ui. Okay, and therefore you know that this is b transpose, this is ui. Maybe I should write it in a more easier, more straightforward case. So this one becomes your b transpose, this one becomes your ui. Okay, and therefore your stress is equals to this one. Alright, so this, in other words, you're somewhat changing your strain in terms of all this stuff. As you can see, your strain becomes such of a big chunk of information over here. Okay, so therefore this is just a quick understanding of the stress of the bar. Okay, this is the stress for a bar, with a bar like this. Okay, for stress for a beam, for stress of other stuff, this thing over here will change because you have a different form of displacement. As you can see, the key step over here is this one, where you sub in your U is equals to this thing. So for different scenario, you have a different equations to represent your U. Alright, so this is the key concept that I just want to compare. I repeat again, please remember that for different situation, for our situation this is a bar, therefore we use this one. For different situation like other stuff like beam, like Martian, I don't know anything, but anyway, so you have a different equations. Alright, we got other stuff, and then once you have different other equations, you just simply sub it as your U over here, and then you evaluate like what we have evaluated, and I should believe that you have some other stresses in terms of some other stuff over here. You may have other long stuff, but it's all in terms of the strain. Alright, but the Young modulus doesn't change and the stress doesn't change. Alright, just the formula within the strain itself is pretty much very hairy. And therefore I'll leave you to this, and in the next video we'll talk about the principal virtual displacement. See you there.